We often divide a contact force into two components. The normal component is in the normal direction. The component of a contact force in the plane of the surface is what we call friction. Fundamentally, there is only one force, the contact force. Dividing it into its normal and frictional components is arbitrary, but it turns out to be very useful. In fact, we'll find out that it's often the first step in solving problems involving contact forces. But what exactly is friction? Well, on the macroscopic scale, this looks like the interaction of two flat surfaces. But on the molecular scale, it looks like taking Austria and putting it upside down on top of Switzerland. The surfaces are only in contact on a small number of small areas. But in these areas, the force per unit area can be so large that they spontaneously weld together. When we try to slide the surfaces, these microscopic mountains bump into each other and even shear off. So, at a molecular level, friction is complicated and there are only approximate laws for its behaviour. We'll meet a couple of these. But first, we make a distinction between two different cases. When there's no relative motion between the surfaces, we call it static friction. When there is relative motion, when one surface slides on another, we call that kinetic friction. Let's do an experiment. Here's a 1.0 kilogram mass. It's not accelerating in the vertical direction, so the vertical forces add to zero. So the magnitude of the normal force between the two surfaces is mg, which is, to a good approximation, 10 newtons. I now apply a horizontal force, gradually increasing it until it starts to move. From the last video frame before it moves, we can read the applied force. Now I try 2 kilograms, same surfaces in contact. This time the normal force is 20 newtons, and again we read the force from the video frame. Well, we continue this to plot the limiting friction versus the normal force. Empirically, we see that the limiting friction in the static case is approximately proportional to the normal force. The constant of proportionality is called the coefficient of static friction, mu sub s. Here's an important point. It's static friction whenever there's no motion, so the frictional force Ff can be anything from 0 up to the limiting friction, mu s times n. Remember that it's an inequality, not an equation. Make a note of that. Now back to our experiment, and this time we look at the case of kinetic friction. We measure the constant horizontal force required to drag the masses at constant velocity. Constant velocity, so the total horizontal force must be 0 in this case too. So the magnitude of the frictional force equals the magnitude of the applied force, 0 total force. Starting again with one mass, but now reading the force required to keep it moving at constant velocity. Let's plot those data on the same plot. As with limiting friction, we see that kinetic friction is approximately proportional to the normal force, and this time the slope gives what we call the coefficient of kinetic friction. We also notice that for these two surfaces, mu k is a bit less than mu s, and that's usually the case. Coefficients of friction are rarely much greater than about 1. Let's summarise that. If there's no relative motion, we have static friction, and the friction force is less than or equal to mu s times n. If there is relative motion, i.e. sliding, then the friction force is mu k times n. Finally, mu s is usually a bit higher than mu k. Limiting friction is usually larger than kinetic friction. So it takes a bigger force to get something moving, but usually a smaller force to keep it moving. Let's get quantitative. My mass is 72 kilograms. The coefficient of static friction between my shoes and the floor is 1.0. So, what is the frictional force the floor exerts on my shoes?